In the previous lecture of this series, we talked about the nature of light. In this lecture, we will discuss Huyghens Principle as well as Huyghens Fresnel Principle. In the previous lecture, we discussed about the fact that light is a wave. It is a transverse wave. It is an electromagnetic wave, as well as it had other features, the photon character, etc. Just for recapitulation, the electromagnetic spectrum is presented here. This is the lambda column, frequency column, energy per photon, and we see that the gamma ray is the most energetic one, while the radio wave is the least energetic one. The wave representations are given over there. From here it is clear that the undulations or the oscillations are very frequent for gamma ray, while for radio wave it is very infrequent, and the wavelength therefore is large. And the most important fact is that gamma ray has a photon which is extremely energetic, and therefore it is more a particle. On the other hand, a radio wave is more a wave, its photon being less energetic or least energetic. And visible ray, which will be the main topic of discussion, lies in between, and therefore it exhibits wave particle duality. Just for academic purpose, let me present the wavelengths of visible light. This is the short wave, violet, and red is the long wave. Violet has lambda 4000 angstroms, while red has 7000 angstroms. Now, Huygens theory says that light is a wave. Now let us be very clear about one thing now. We spoke of electromagnetic theory of light propounded by Maxwell, and we also spoke about Huygens wave theory. Now, what will we be discussing in physical optics? It should be very clear that we will not be discussing the electromagnetic wave theory under physical optics. Under physical optics, we will be discussing the wave theory and not electromagnetic wave theory. Now, Huygens theory is about wave. Light is a wave, and wave is a disturbance that moves through a medium. Now, to describe a wave, we need the idea of wavefront, and when a disturbance passes through a medium, not all points are similarly affected, but some points are similarly affected. So we can consider, or we can imagine, a surface that passes through the similarly affected points. Then that surface is referred to as wavefront. So wavefront is a surface or a region over which the wave has same phase. In case of a lens, this is the plane wave and this is the spherical wavefront, and we know about an important feature that the ray is perpendicular to the wavefront, as evident from these 90 degrees. Let us now speak of various types of wavefront. The various types of wavefront may be spherical wavefront, it may be cylindrical wavefront, and plane wavefront. So first, let us consider spherical wavefront, that is generated due to pulsations or oscillations of a point source. So a point source that is oscillating in space generates disturbances in all directions, and points which are equidistant from this source point are similarly affected, and therefore we have spherical wavefronts. Now these spherical wavefronts propagate in space and at a large distance reduce to plane wavefronts. In a similar way, if we have a line source and it pulsates, it oscillates, then it will generate or give rise to cylindrical wavefronts. So these are successive or rather consecutive cylindrical wavefronts that are moving over space, and at a very large distance these cylinders become plane wavefronts. Now to discuss this point, let us consider this diagram where we have shown a small circle, and this circle has a large curvature, but its radius of curvature is very small, and this is the relation between radius of curvature and curvature. They are inversely proportional. So if curvature is large, then radius of curvature is small, but in this case, in this surface, the curvature is small, so the radius of curvature will be large, and in the limit for a straight line which is not at all curved, the curvature is 0, but the radius of curvature is infinity. And also if we draw perpendiculars, for instance here if we draw perpendiculars at 2 points, they will meet at the center. Here if you take 2 points and draw perpendiculars, then those lines will be parallel and they will meet at infinity. So curvature is 0 means radius of curvature is infinity. The similar thing happens in these cases also. Another important thing that is to be mentioned is that a very small portion of a curved surface can be treated as a straight portion. Now here what happens is, at a very large distance the curvature goes on decreasing and ultimately they become plane waves. Here too, these cylindrical surfaces after traversing a large distance become too large and the curvature becomes very small, and so they are essentially plane waves. Another way to look at the same thing is that if we are at a very large distance, if the observer is at a large distance from the source, then a very small portion of this wave will pass through the observer, and that small portion can be treated as a plane wave. So these are the two pictures. And also let us mention here that the intensity is proportional to amplitude square in both the cases. In spherical wavefront case, the intensity is proportional to 1 by r square. We'll explain it later. Amplitude is proportional to 1 by r. But in cylindrical case, the intensity is proportional to 1 by rho and the amplitude is proportional to 1 by under root rho. Here r is the radius of the spherical wavefront and here rho is the radius of the cylindrical wavefront. Now, for a plane wave, however, intensity does not depend upon distance, amplitude also does not depend upon distance, because a plane has been achieved, curvature is 0, but here the curvatures are continuously decreasing. So wavefronts grow in size with time, curvature reduces, distance from source increases, and we end up with plane wave, though we are starting with a spherical wave or a cylindrical wave. Let us think of the waves that are coming to us from the sun. The sun is emitting spherical wave, and the wave that reaches us on earth is actually plane wave, because a very small portion of the wave is passing through it, and therefore we can treat it as a plane wave, because here the distance is infinity. Actually the distance is very large. So we have made a gist of the various relations, I for intensity, A for amplitude, and as stated we have put it in a table for convenience. Let us now consider the propagation of a plane wave front along x cap first. So we are taking a particular direction along which a plane wave front is propagating. The plane wave front has this type of structure where this is the phase, kx minus omega t is the phase, and kx can be written as kx cap dot x cap x, which means that the propagation direction is vector k, which is along x cap, and k is related to lambda through this relation. It is actually a vector quantity. It is called propagation vector. It represents propagation of the wave along x direction. Now we are speaking of wave front. In Huyghens theory we will be dealing with wave fronts, so we should have a good idea about this wave front. What is the equation of a wave front? The equation of the wave front is the phase of a wave should be constant. That gives the equation of a wave front. Wave front are surfaces of constant phase. So the equation of plane wave front for this situation where a wave is moving along x direction is given by this phase part is constant, so we have kx minus omega t is constant. It represents surface of constant phase. Now at some specific time, say t equal to t1, we'll put t1 for t to end up with this equation. Now omega t1 is a constant because for the wave omega is constant and t1 is some specific time, so we have kx minus omega t1 as constant. If this part is constant, then we end up with kx constant. Again k is a constant, and therefore we end up with x constant. Now x is constant means, say the value of this constant is x1, some x1. This means we have plane wavefronts because x is constant, there is no distortion, x is constant, so we have plane wavefronts. Now this is x1 at time t1, and similarly we can have another x2 at time t2. Now interesting thing is that kx minus omega t is constant, that defines the wavefront. If t rises, then to keep kx minus omega t constant, one should have to increase x. This, in other words, mean that the wavefront is moving, because x rises means the wavefront is advancing along x cap. So wave moves along x cap and the direction of propagation and wavefront are perpendicular to each other. What if the propagation occurs along any arbitrary direction? So this is the picture, x cap, y cap, z cap are the unit vectors, and this is the direction of propagation of the wave, and these are the plane wavefronts. So in this situation, the 3D propagation, earlier one was 1D propagation. So in this 3D propagation case, this is the equation of the wavefront. As before, this is the phase, and here k dot r, vector r, is given by this expression where vector k has been dissolved into 3 unit vectors and vector r is this amount. If you take the dot product, we end up with this vector, we end up with this relation. Now the equation of the plane wavefront is, this one is constant, so we have k dot r minus omega t is constant, which represents surface of constant phase, in other words wavefront. At any fixed time t equal to t1, this factor is constant. As in the previous case, omega t1 being a constant, we end up with k dot r constant, and this gives us this factor to be constant. Now this is actually the equation of a plane, the plane we are speaking of, that is the plane wavefronts, and here too k is perpendicular to the wavefront. The last case which we will be discussing before going to Huyghens principle is propagation of spherical waves. Now this is a point source which emits light in all directions, and this is the spherical wavefront. Now here the direction of propagation of the wave is along the radial direction, so it is vector k is k into r cap. Now the wave function or the equation of the wave is given by a by r cos of a phase factor. Now why does 1 by r come here, we will discuss soon. As before, the equation of the spherical wavefront is this part is constant. Now if we put the values of k as k into r cap, and vector r is obviously r into r cap, so r cap dot r cap is 1, so we end up with this relation, which is set equal to constant, because we are discussing the equation of a wavefront which is surface of constant phase. As before, at t equal to t1, this part is constant, so we are left with kr equal to constant. Now for this source, k is constant. For this wave set of waves, k is constant, and therefore kr constant leads us to r constant. So r is constant means we have surfaces of constant radius, so we have spherical wavefronts. And if we consider the equation kr minus omega t equal to constant, and as t rises, to keep this one constant, r also has to rise. This again means that wave advances along r cap, because only if wave advances along r cap will have an increase in r. So wave expands outwards as spheres. So what we essentially have in this situation is expanding spheres. Now a very important part of it is, over the entire wavefront or the spherical wave, energy is distributed, and this wave, this sphere, is expanding. Now over this wavefront, the energy that is spread out or distributed is constant, so energy is conserved. Now let us consider the intensity. Now intensity is power by area, and power is energy by second, and energy is constant. So what we have is intensity is constant by area, and area is 4 pi r square of this spherical wave having radius r by second. So what we have is intensity is proportional to 1 by r square, and therefore the amplitude is proportional to 1 by r, as we had previously in this equation. So this is why here we have a by r, but in case of plane wave we just had the same thing without 1 by r. So I proportional to 1 by r square follows from energy conservation. In the cylinder case, the same formula leads to a different result, because area in case of a cylinder is 2 pi rho the base circumference into the length, so it is 2 pi rho into L, and therefore the intensity is proportional to 1 by rho, and from here it follows that the amplitude is proportional to 1 by under root rho. Let us now come to Huyghens principle. First, why is it used? The Huyghens principle is used to determine the shape of wavefront at any future time through a particular geometrical construction. What is the statement of Huyghens principle? The statement consists of 4 points or parts, which will come one by one. The first part says that a source of light emits primary wavefront in all directions. The second point says that every point of the primary wavefront is again a source of fresh disturbance. So this is the source, and a primary wavefront has been emanated from it. Again, this primary wavefront is built out of infinite number of points. Every point is a source of secondary wavelets. So from this point we get the idea of two types of wavefront. One is directly emitted from the original source, and the other one are the wavelets or the waves that are emitted from points on the primary wavefront. So we have two types of waves, primary wavefront and the secondary wavefront. Third point is these secondary wavelets or secondary waves travel with the same speed as that of the primary wave in this medium. The fourth point is that the common tangent plane, which is also called the envelope, in the forward direction, that is along the ray direction, will be the new wavefront. So suppose we consider a plane wavefront. Here is the source, and at a large distance we have a plane wavefront. This is the position of the primary wavefront at time t1, say. Now we are interested to find what will be the position of the wavefront after some time, say delta t, that is at t1 plus delta t. The procedure of construction, procedure of obtaining this position of new wavefront is given by Huyghens principle. So according to the principle, this primary wavefront is built out of several points and each is a source of secondary waves. So this is a secondary wavefront which is spherical. This is another secondary wavefront which is also spherical and emitted from this point. Similarly, this is the third one which is emitted from this point. And similarly, we have infinite number of secondary waves that are generated from these infinite number of points of the primary wavefront. Now the radius of these spheres will be v into delta t, v being the speed of the wavefront and delta t is the time after which we want to know the position of the wavefront, primary wavefront, and then we have to join these points. So this is the common tangent plane or the envelope. So this will be the position of the new wavefront. If we come to the spherical wavefront case, so this is the source, and at some time t1, this is the position of the primary wavefront. Now taking these points as centers, we can draw spheres like this which represent secondary wavefronts, and these spheres have radius v into delta t because we are interested to find the position of this primary wavefront after time delta t. And if we draw the common tangent plane or the envelope, then we end up with the new position of the primary wavefront after time delta t, that is at time t1 plus delta t. So this is the procedure of getting the position of primary wavefront at a future time. Now very important point is we have to draw the forward envelope and not the backward envelope. Here also the forward envelope is to be taken and not the backward one. This is because energy propagates from source in the forward direction and not in the backward direction. So if this is the position of the primary wavefront, then after time delta t, the wavefront will not move towards the source but move forward. So this envelope, even if we draw it, is of no significance. It does not represent the real wavefront, and that is why in Huyghens principle this wavefront, this envelope will not represent a wavefront, a real wavefront. So this back wave has to be eliminated, and therefore in the principle it is said that we have to take the envelope in the forward direction. Next, let us try to find the position of the primary wavefront after a further time of delta t, that is after, say, time twice delta t. This can be done in two ways. Suppose this is the position of the primary wavefront. Now, with various points as center, we can draw spheres of radius v into twice delta t, and then as before we can join these points. The envelope can be constructed, which will give us the position of the primary wavefront after time t1 plus twice delta t. Or the same wavefront can be obtained in two steps. The first one is we can draw secondary wavelets, secondary spherical wavelets of radius v into delta t to arrive at the position of the primary wavefront at time t1 plus delta t, and then repeat the process by constructing secondary spherical wavelets at various points as center of this primary wavefront at t1 plus delta t, and then draw the envelope to get to this position. Now, Huygens assumed that the amplitude of the secondary wavelets will be non-zero only in the forward direction. So if we consider the plane wave here, these are the secondary wavelets, and the amplitude here or at this point will be non-zero. So these reinforce and we have a forward moving wave. Now what about this direction? The amplitude along this direction will be 0 as per Huygens principle. If we consider to this diagram, which consists of spherical wave propagation, this is a ray direction. So the amplitude at this point of the spherical wavelet will be non-zero. So this will contribute, and similarly this one will contribute. These points all will contribute, and therefore we end up with this primary wavefront. But if we take this direction, then there will be no contribution along this line. So amplitude is 0 here. Now this statement, this fact can be summarized in this diagram. This is the secondary wavelet and this is the primary wavefront. This is the ray direction. So according to Huygens principle, there will be contribution along ray direction. So this point will be effective, this point will contribute, but a direction at an angle theta will not contribute. So amplitude along this direction being 0, there will be no propagation along this direction. So secondary wavelets contribute only along the forward direction, which in our diagram is theta equal to 0. Let us make certain comments. Huygens principle, as we stated elaborately, explains rectilinear propagation of light. So this is evident because the secondary wavelets contribute only in the forward direction. So forward direction means theta equal to 0, where amplitude is non-zero or finite, while in other directions corresponding to theta not equal to 0, the amplitude is 0, that is, there will be no contribution of the secondary wavelets. So in a nutshell we can say that the ray moves forward, and this is rectilinear propagation. Another point which is very important and strikes in our mind is Huygens' assumption is ad hoc and has no basis, because the secondary wavelets contribute only in the forward direction. How is this possible? we do not get any explanation of this fact from Huygens principle. So Huygens assumption is arbitrary and has no basis. And why was it done? The assumption was correct, though it has no basis, and the correctness of assumption is because energy cannot flow back to the source. It has to move away from the source. So the assumption was correct, but Huygens was not able to give an explanation for it or a basis for it. The assumption was done to eliminate the back wave, because if this is a source, the waves cannot move towards the source. So to ensure that, this type of assumption was made. Now that only one point of secondary wavelet along theta equal to 0 is active is not explained. Why does other point not contribute? This is not clear. So this is the drawback of Huygens principle. We can sum up by saying that in Huygens principle, therefore, two mechanisms are not clear. One is generation of the forward primary wavefront, because to generate forward primary wavefront, Huygens principle assumes that in the secondary wavelet only one point is effective. What about the other point? Why aren't they effective? And secondly, mechanism of elimination of back wave is not clear, because according to Huygens principle, we have to draw the envelope only in the forward direction and not in the backward direction. That was experimentally alright, but the basis is not evident here. So the mechanism of elimination of back wave is not clear. This, however, was explained later by Fresnel, and therefore let us mention Huygens-Fresnel principle now. Huygens in 1678 stated the Huygens wave theory, while Fresnel modified it in the year 1816. And the statement of Huygens-Fresnel principle is as follows. Huygens principle is every point of primary wavefront is a source of fresh disturbance, is a source of secondary wavelets, and according to Fresnel, the secondary wavelets mutually interfere. This is also called diffraction part. Now this part was introduced by Fresnel. So the phenomena of interference come into the description. This will deal later, interference and diffraction. So the idea is, we have a primary wavefront here. According to Huygens principle, each point is a source of secondary wavelets. So these are the secondary wavelets. These are small waves that are emanating from this primary wavefront. Now what do? They mutually superpose and interfere, and the interference might be constructive or destructive. The explanation is as follows. The primary wave moves forward because the secondary wavelets reinforce in that forward direction, and this is constructive interference, due to which primary wave advances. The primary wave does not move backward because the secondary wavelets oppose and destroy each other in the backward direction. This is destructive interference, due to which primary wave carries energy not in the backward direction but in the forward direction. In our context, therefore, along theta equal to 0, which represents the ray direction and which is the direction along which energy moves, the wave moves. Constructive interference between the secondary wavelets help it to move forward. But for all other directions, theta not equal to 0 and as well as the backward direction, the secondary wavelets interfere destructively, cancel out, and therefore there is no question of energy being propagated in the backward direction. So this explains backwave elimination. A better argument was later given by Fresnel, and we'll just make passing comments. Fresnel introduced later the concept of half-period zones, and with it he explained rectilinear propagation of light. This will be discussed later. Now, backwave elimination can be done under diffraction theory. So the amplitude of secondary waves can be calculated, and it can be shown that it contains an obliquity factor. It contains a factor half into 1 plus cos theta, which is called obliquity factor. This means that the amplitude of secondary waves depends upon theta. It is not same in all directions, as evident from this diagram where we have a secondary wavelet. Now this is the forward direction and this one is the backward direction. At theta equal to 0, that is in the forward direction, we have the value of obliquity factor to be different from 0, because if we put theta equal to 0 here, then cos 0 is 1 and therefore we have 1 which is not equal to 0. So in this direction we have a strong forward wave. On the other hand, in the backward direction, which corresponds to theta equal to pi, the obliquity factor gives a value which is 0, because cos pi is minus 1. So this leads to elimination of the back wave. So the obliquity factor is able to explain a strong forward wave as well as the elimination of a wave which is called back wave. The application of Huyghens principle is the next topic. Light passing through aperture, this will be taken up. Reflection, refraction, these phenomena, how are they explained with the help of Huyghens principle? These will be taken up in a future lecture entitled 2b, while a very important experiment was done by Young, named Young's two-slit experiment, that we will be discussing in lecture 3a. Let me wind up this discussion with a quote of a famous physicist, John Tyndall, an Irish physicist. Life is a wave which in no two consecutive moments of its existence is composed of the same particle. Yes, life moves like a wave. There are crests of joy and troughs of despair, but we have to move on stoically. Thank you.